Right, so in the last few videos, we looked at combinatorics, but maybe, it's worth looking back to what we were doing before that, and namely, we looked at divisibility and problems that have to do with divisibility. And so that's what we're going to keep doing, and it's worth looking back at those divisibility videos because we're going to use some results from those to do some of the proofs in this video. So if you're not comfortable with those videos, maybe look back at them. So what we're going to do is we're going to expand on this by introducing a convenient tool, to talk about general divisibility in the format of quotient and remainder. So we already looked at the quotient and remainders of division. And so now we're going to introduce ways to talk about this by using a really nice notational tool called modular congruences. So yeah, this tool is known as modular congruences. And it's really a language more than anything, and it's the main language behind a lot of elementary number theory, so it's a good idea to have a good grasp on it before we go further. So what are modular congruences? So let's define them. We're going to let a, b, and m be integers with n not equal to 0, and we're going to say that a is congruent to b modulo m, and we write that as a equals b mod m. This is not an equal, it's 3 lines, and we say a is congruent to b. So make sure you don't make that mistake if you ever write that down, not to write an equal sign because it's not exactly the same relation. So it's written a 3 bars b mod n, a is congruent to b modulo n. And so this is only true, well, it's true if and only if m divides a minus b. So m divides the difference of a and b. Let's look at some examples. So for example, we've got that 10 is congruent to 1 mod 9 because 9 divides 10 minus 1 because 10 minus 1 is 9. We've also got that 13 is congruent to minus 1 mod 7 because 7 divides 13 minus minus 1 because 13 minus minus 1 is 14. And we've got that 27 is congruent to 0 mod 3 because 3 divides 27 minus 0, which is 27. So you'll note that if a number is congruent to 0, then that's exactly when this modulo divides the number. So that's going to be a useful little tool. So, one way to look at this is the official definition, but it might be nice to think about it in terms of remainders. And specifically, we're going to say that a is congruent to b mod m if and only if a and b leave the same remainder on division by m. So we're going to prove that because it's a good way to think about it. And if you look at those examples here, you'll notice that 10 divided by 9 is 1 remainder 1, and 1 divided by 9 is 0 remainder 1, so they have the same remainder. 13 divided by 7 has a remainder of 6, minus 1 divided by 7 has also a remainder of 6 because it's minus 1, and then we add 6. It's kind of an extension of the whole idea of remainder and quotient, where the quotient can be negative. And then we've got that 27 has a remainder of 0 when it's divisible by 3. Okay, so let's look at the proof. So we're going to write them in quotient remainder form that we've seen in the divisibility videos. So we write a equals qm plus r, where q is the quotient and r is the remainder, and b equals q dash m plus r dash. This time q dash is the quotient, r dash is the remainder. And so of course we've got that r and r dash are between 0 and m minus 1. So they inclusive. So they can be 0, they can be m minus 1, but they have to be in that range. So in that case, we've got that a is congruent to b mod m, if and only if m divides a minus b, and so that's just the definition here. So that's if and only if a minus b equals mk by definition of divisibility. And so, we can rewrite a and b as qm plus r, so that we get qm plus r minus q dash m minus r dash equals mk. And so if we rearrange things a little bit, we can bring the qm and the q dash m to the other side to get m times, well, the mk to the other side actually, to get m equal times q minus q dash minus k. If we change the signs, well, if we subtract the whole equation by mk. And I can add r dash and I can subtract r to get r dash minus r on the right hand side of the equation. So that's how we get this step here. And so because of the inequality on r and r dash, we have that m divides r dash minus r. If and only if, we only have that m divides r dash minus r if r equals r dash. Because note that r dash and r are between 0 and minus 1, So for difference has to be between 0 and -1 as well. And m can only divide a number smaller than itself if that number is 0. And I mean, a number smaller than itself than is positive. That's only if that number is 0. Because the absolute value of the difference of r dash and r is going to be m minus 1 maximally. So yeah, only when r and r dash are equal to each other, and then we can get that r dash minus r is 0, and then m can divide it. And we note that here, this inequality, this equation here is really saying that m divides r dash minus r, because this here is an integer. So hence, the remainders of a and b upon division being the same is equivalent to a being congruent to b mod m. You know, we've done this line of reasoning only with if and only if statements. So it's an equivalence between congruence and having the same remainder. So now that we've got that, let's kind of jump back to a little more abstract way to think about modular congruences. We're not going to dwell on it for too long, but it's just a nice little tangent. So I'd like you to remember that relation R is an equivalence relation if and only if it's reflexive, symmetric, and transitive. And so if you don't remember that, and maybe you don't even remember what a relation is, refer back to video 4, where we talked about the beginning of combinatorics, and we talked about some counting tools in abstract set theory. So for an equivalence relation R on a set A, we're going to define the equivalence class represented by A, which belongs to big A, as the square brackets around small a is equal to the set X, where X belongs to big A and A are X. So what that means is that this set here includes all the elements of the big set A that are related to A, so are related to A via this relation R. And so note that for any element X that belongs to the equivalence class of A, then the equivalence class represented by X is the same as the equivalence class represented by A. And that's due to the symmetric attribute of a relation, right? Because A are X if and only if X are A. And so, you know, if we look at the equivalence class represented by X, then this will be the condition that we have here. So hence, you know, any element of the equivalence class is called a representative because they can all represent the same equivalence class. And so intuitively, equivalence classes are kind of a way to formalize grouping elements of a set by equivalence. And so we just put elements of a class, elements of a set together in the same class if they're in some sense the same. And that's why, for example, you know, equality is an equivalence relation. And so that kind of helps us to think about what modular congruences really mean. Is that in some sense, any numbers that are congruent are kind of the same. And that's because they leave the same remainder. And that in that sense, they're the same numbers because they leave the same remainder. So we kind of reduce the integers to only thinking about remainders instead of the integers as a whole. So it allows us to perform math on equivalence classes instead of individual elements. And so that allows us to argue generally about a whole bunch of elements by only looking at one equivalence class, or equivalence classes on their own, because any element can represent the equivalence class. So if we only argue about the equivalence class as a whole, then we can argue about all the elements that are in it. So modular congruences are an equivalence relation, as I said before, and we're going to prove that. And remember, you know, the definition of equivalence relation, we've got that it's reflexive, so we've got that A is congruent to A mod M. We've got that if A is congruent to B mod M, A congruent to B mod M if and only if B congruent to A mod M, and that's means that it's symmetric. And we've got that A is congruent to B mod M and B is congruent to C mod M implies that A is congruent to C mod M. This here is just the logical end, okay? So that's a transitive relation. So the proof is pretty simple. So for 1, we just note that, you know, A is congruent to A mod M if and only if M divides A minus A, and A minus A is just 0, and M divides 0 by, I mean, that's easy. So for 1 is easily proved. For 2, we can note that A is congruent to B mod M if and only if M divides A minus B, once again by definition. And remember that we can take the negative of this side and M is still going to divide it. So M divides the negative of A minus B, which is B minus A. So, and that's if and only if B is congruent to A mod M, because by the same definition again. So we've got that A is congruent to B mod M if and only if B is congruent to A mod M, and that proves that part. And then for 3, we'd like to note that if M divides A minus B and M divides B minus C, so that's just the definition of these two, then by linearity of divisibility, and so refer to video 2 for that, or the end of video 1, then m divides a minus b plus b minus c. And so if we expand that, we've got minus b plus b, that's going to be 0, and we've got a minus c in the end. So we get m divides a minus c, which implies that a is congruent to c mod m. So that's that part proved. And so that proves that modular congruence is an equivalence relation. So the integers modulo m. So since congruences are equivalence relations on the integers, we can construct equivalence classes. So since we know that two numbers are congruent mod m if and only if m divides their difference, we can simply, start from 0, take all the numbers that are a multiple of m away from 0, because then when we subtract them, we're going to have a multiple of m, which means that m divides that difference. And so all the numbers that will be a multiple of m away from 0, that's going to be one of the equivalence classes. We can do the same for 1 and for 2, and we can go on until m minus 1. Because once we reach m, then taking all the numbers that are a multiple of m away includes 0, and so m is really in the same equivalence class as 0. So we're therefore left with a set, with m sets, which partition the integers. So in general, and that's not something we've proved, but it's not too hard to prove either. In general, equivalence classes are going to partition a set that they're on. And actually, you can make a stronger statement, which says that any partition is related to some equivalence relation, and any equivalence relation is related to some partition. So we're not going to prove that because this isn't, a video series on relations, but it's a nice thing to note. So these numbers are known as the integers mod m. We take one representative from each class, right? And those will form the integers mod m. So let me tell you what I mean by that. We're specifically going to consider the representatives that are between 0 and m, right? So I've got 0, I've got 1, and so on until the representative class for m minus 1, like that. And basically what we do is we say, okay, group these guys into one set, which we're going to call Zm. Now this is super important for group theory. A lot of group theory, if you have heard about group theory, can somehow be analogated to doing some things in Zm. And that's elementary number theory is very tightly grouped, very tightly linked to group theory. And so you can learn a lot about group theory just from doing elementary number theory. And so basically what we do is you can now just kind of forget about these square brackets and only consider the numbers 0, 1, 2, 3, 4, all the way to m minus 1. And then you can do operations on these guys. So I'm just going to show you this here. We can draw the square brackets and specify what we're working in mod m, right? And then we can do arithmetic on integers mod m. So the arithmetic is the same as for regular integers, except at the end you're going to replace a number by a representative of its equivalence class between 0 and m minus 1. So for example, if I do m minus 1 plus m minus 3, right? That's going to be 2m minus 4. But however, note that 2m minus 4, if I consider the number m minus 4, then 2m minus 4 minus m plus 4, so minus m minus 4 basically, is just going to be m. And so m divides m, right? Which means these two guys are congruent mod m. And so that means they're in the same equivalence class. So at the end of this operation, I'd reduce down to m minus 4, and that will be the answer of m minus 1 plus m minus 3. That would be m minus 4. And that's true in the integers mod m. And so you can do a lot of cool stuff with that, like order and all that stuff. But we're not going to get into that right now. It's just a nice thing to mention. So, congruence arithmetic. It's time to actually do some math with modular congruences. So congruences are pretty familiar to work with, in many cases, because they actually follow some of the usual rules of arithmetic. And, namely, if A is congruent to B mod M and C is congruent to D mod M, then A plus C is congruent to B plus D mod M, and that's kind of the same as saying A equals B and C equals D, then A plus C equals B plus D, and we know that's true for equality, but we have to prove that for congruences. And actually, we can do the same with multiplication. A times C is congruent to B times D mod M. So to prove that, it's not a very interesting proof. We're just going to be crunching the numbers. And so we've got that A is congruent to B mod M and C is congruent to D mod M if and only if A equals B plus MK and C equals D plus MK dash. So A equals B plus MK, that's the same as saying A minus B equals MK, which is the same as saying that M divides A minus B. So this is just another way to write it. And this is the same thing here. And so these guys, K and K dash, are indeterminate. And so that implies, because here we have equality, and we know how equality behaves when we do addition and when we do multiplication. So I can add these two to get A plus C equals B plus D plus M times K plus K dash. And I can also multiply these two to get A times C equals, and then I have to FOIL this out to get B times D plus M times BK dash plus DK plus MKK dash. I'm not gonna dwell on the math behind this. I mean, it's simple foiling and it's not very interesting, to be honest, so we're just gonna keep going. So then we have that A plus C minus B plus D equals M times K plus K dash, and we've got the same for multiplication, and so that's exactly what we want. We've got the M divides the differences, so we've got the congruences that we were looking for. However, I want you to note that what is not true, well, first of all, let's note what is true. From these two, one very nice consequence is, first of all, you can note that from multiplication, what we actually have is that if A is congruent to B mod M, then for an integer, well, for a natural number k, we've got that A to the k is congruent to B to the k mod M. Now you can prove this rigorously with induction, which we're not going to do, but it's a really simple inductive argument by using the multiplication property. Now what's not true is that if we've got A is congruent to B mod M, and we've got that C is congruent to D mod M, what is not true is that I cannot take powers. I cannot say C to the A is congruent to D to the B mod M. That's a trick that's a habit you might want to get into sometimes, but never do this, because this is not, most of the time this isn't true, and it's just going to give easy mistakes that you don't want to do. Now we can generalize even further from this here. We can generalize further by actually saying that any polynomial with integer coefficients, f, if f is a polynomial with integer coefficient, and we've got that A is congruent to B mod M, then actually f of A is congruent to f of B mod M. And we're going to use that fact a little bit later. So keep that in mind, because that's pretty important and can allow us to do some pretty general arguments. Alright, moving on. So inverse is modulo M. So, proposition. If the greatest common divisor of A and M is 1, so if they're coprime, then there is a unique integer A to the minus 1 mod M, such that A times A to the minus 1 is congruent to 1 mod M. Now A to the minus 1 is not necessarily the same as 1 over A, because keep in mind, these, technically speaking, these guys here that we're considering, you can kind of think of them as the integers mod M, and this division here isn't defined on the integers mod M. And even when we're working on integers, just inverses aren't really defined like that, because, I mean, we've already seen that there's problems with divisibility like that. So that's why here we have to be specific about just considering a new number called A to the minus 1. This is just a notation for it. And so in mod M, it's going to be such that A times A to the minus 1 is congruent to 1 mod M. And when I say it's unique mod M, it means that all the numbers that satisfy this property here are congruent to each other. So if A times A minus 1 is congruent to 1, and A times B minus 1 is congruent to 1, then A to the minus 1 is congruent to B to the minus 1 mod M. Okay, so let's prove that. Well, the greatest common divisor of A and M is 1, and so by Bezout's lemma, if you remember that, we've got that there exists an x and a y that belong to the integers, such that ax plus my is equal to 1. That's the linear combinations that we've seen. Now what does that imply? That implies that ax minus 1 is equal to m times minus y, and we've just moved things around. So that implies that ax is congruent to 1 mod m, right? If we just have minus 1 minus y here as a multiplication to m. And so m divides this. And so if we set a minus 1 is congruent to x mod m, right, then that's going to show existence. Because we've got that a times x is congruent to 1 mod m, so we know that at least the inverse exists. Because we know that x exists given by Bezout's lemma, and we've proved that before. Now we actually want to show uniqueness as well, so let's consider an alpha 1 and an alpha 2 that satisfy the same property. And so by transitivity of this, we're going to have that a alpha 1 is congruent to a alpha 2 mod m. So that implies that m divides a times alpha 1 minus alpha 2. Okay, so I think I just didn't have an animation for what's coming next. So I'll just write what's left, right? So we've got that m divides a times alpha 1 minus alpha 2. Now one thing we'd like to note is that the GCD of a and m is 1, right? Which means that m, if I can write that, yeah, if m going to divide alpha 1 minus alpha 2. And so that means that we've got that we've got that alpha 1 is congruent to alpha 2 mod m. I'm not sure why PowerPoint is messing up. Mod m. Mod. Okay, well, whatever. So that's completes the proof. So let's move on. We've got simple divisibility tests that we can do with congruences, and that's more of an application. So let's consider the base b representation of a number n. Right, and so the base b representation of the number n is going to be the sum from I equals 0 to k of ai b to the I. And so you can refer to the last video where we looked at base b representations of numbers. And so let's say that b has a prime factorization p0 to the e to the 0, p1 to the e1, all the way times pm to the em. Okay? Then we're going to claim that n is congruent to a0, which is just the first digit, right? Mod p0 to the alpha 0, p1 to the a1 times pm to the alpha m, where we've got that any alpha I is between 0 and ei. So basically, if I take any factor of b, then n is congruent to a0 mod that factor. So proof. First, we're going to consider the polynomial, the general polynomial, fx equals the sum from I equals 0 to k of ai x to the I. And so the a's are defined, as here, from the base b representation of n. And x is the variable for a polynomial. Now, these are integers, so it's a polynomial with integer coefficients. So note that we've got that b is congruent to 0 mod this whole thing, because this whole thing is a factor of b. If we can just multiply each of these by some power of p of the prime to get to b. So this divides b, which means b is congruent to 0. And so hence, by what I said before about integer polynomials, we've got that f of b is congruent to f of 0, mod that same factor. However, note that f of b is equal to n, because f of b just gives us this sum over here if I plug b into x. And f of 0, if I plug 0 into x, right, then I'm going to get 0 to the 1 and 0 to the 2 and 0 to the 3. All those guys are going to go to 0 and disappear. But 0 to the 0 is going to give us 1. And so I'm going to have ai, a0, sorry, is going to be a0 times 1. And all the other ones are going to disappear and go to 0. So we're only going to be left with a0. Hence, we've got that n is congruent to a0 mod that factor. Forgot to write that. And so that completes that proof. So I talked about some divisibility tests, but maybe you're wondering how can this help us, more generally, and we're going to see that right after. Waiting for it to load. Okay, so if the number n has base b representation again, then we've got that if b is congruent to 1 mod m, then n is congruent to the sum of its digits in that base b representation, mod m. And if b is congruent to minus 1 mod m, then n is congruent to the alternate sum of its digits, mod m. So let's look at the proof for that. So we're going to consider the same polynomial as last time, and it's going to be a similar proof. So we've got that fb equals n, just like last time. We've got that f1 equals the sum of the digits, because if we just plug in 1 to the I, that's just going to give us 1 for all of them. And then f minus 1 is going to give us the alternate sum, because any odd power, well, an even power, sorry, is going to give us 1, and any odd power is going to give us minus 1 as a coefficient. So it's going to give us that alternating sum. So then the results just follow from the fact that b is congruent to 1 mod m, so that implies that f of b is congruent to f of 1 mod m, and so that implies that n is congruent to that sum, as we need for 1, and that if b is congruent to minus 1 mod m, then f of b is congruent to f of minus 1 mod m, and so that gives us that n is congruent to that alternating sum. So using those two facts from the last two slides, we can have a nice corollary about just division in general when we're speaking in base 10. So here I'm giving the base 10 representation of n, and maybe I didn't even need to specify that, but it's just keep in mind it's just the regular way that we write numbers. Then also in all of these I'm considering for reduced to base, not for general base. So we've got that 2 divides n if and only if a0 equals 0, 2, 4, 6, or 8. And so that means that's if and only if 2 divides a0. So we already know that that's true, because that's only when it's an even number, and we know that 2 divides a number only if it's even. But this is actually due to the first proposition that we proved in terms of the factors. And so the reason we proved that is that it just gives us a more general setting for different bases. But in this case, it gives us a nice corollary for just base 10. And we can say the same about 5, because 5 is also a factor of 10. So we've got 2 and 5 are the prime factors of 10, and so that means that we can apply this for 2 and 5. Now, what about 3? When does 3 divide n? Well, 3 divides n when 3 divides the sum of the digits. Now, why is that? Well, that's because if we look at 10, right, because we're in base 10 here, we'll note that 10 is congruent to 1 mod 3. And so according to the last slide, then we have that 10 is congruent. Well, we've got, that n is going to be congruent to a0 plus a1 plus all the way to ak. Which means, of course, that n minus a0 plus a1 plus ak and all that is going to be congruent to 0. And so that means that 3 is going to divide their difference, and so 3 divides them exactly. And what about 9 divides n? Well, it's the same thing. 10 is congruent to 1 mod 9. And so we get exactly the same result as here. And then we can get a nice one for the other one, and that's 11. So, you might have already heard about the 3 and the 9 tests, but the 11 test is less well known. And we've got that 10 is congruent, to minus 1 mod 11. And so we can apply the theorem for alternating sums. So that gives us a nice divisibility test for 11, which I didn't hear about until quite recently, actually. And it's actually pretty useful for looking at large numbers. So we've got some divisibility tests for those, but we want even more. And so now we're going to consider divisibility tests for 7 and for 13. Oh, I went back a slide. Yeah, here. So let's let n again be in base 10. We're now going to look at a general base for this. We've got that 7 divides n if and only if 7 divides n minus a0 over 10 minus 2 times a0. So n minus a0 over 10, that's just if we consider n as in base b, right? But like you truncate the last digit. You just remove the first digit, you remove the first digit, and then you consider the number that we get with all the other digits. And that's what this n minus a0 over 10 is. And similarly for 13, 13 has to divide n minus a0 over 10, so that same number, but this time minus 9 times a0. So let's look at a proof. So for 1, we're going to let c be n minus a0 over 10 to save us some space, so that n is equal to 10 times c plus a0, just by rearranging this. So this is going to be pretty specific, but you'll have to note that the GCD of 7 and minus 2 is equal to 1. And so from a theory of divisibility that we had before, which you might want to refer to again, we have that 7 divides n if and only if 7 divides minus 2n, because 7 and minus 2 are coprime, we can say this. Therefore, we're going to actually consider minus 2n equals minus 20c minus 2a0, and see what condition we can get for that. And so the condition will also apply for 7 dividing n. So note that we've got that 1 is congruent to minus 20 mod 7, because 1 minus minus 20 is 21, and 7 divides 21. Hence, if I look at minus 2n, which is equal to minus 20c minus 2a0, so I can say minus 1 is congruent to minus 20c minus 2a0 mod 7, because they're the same anyways. And then this minus 20 here, that's going to reduce to 1 mod 7. And so then I've got that minus 2n is congruent to c minus 2a0. And so that means that 7 divides minus 2n, if and only if 7 divides c minus 2a0. Hence, 7 divides n, if and only if 7 divides n minus a0 over 10, so I just plugged in c, minus 2a0. That's what we had here. And so for 13, it's the exact same proof, except instead of a GCD of 7 and minus 2, we're going to have 13 and minus 9. And instead of 1 congruent to minus 20, we'll have 1 and minus 90. So that's just going to be the difference between the two proofs, and that's why I omit it here. So, on that, I just want to give you some homework, because I haven't really been doing that for the other videos, but in general, and especially with number theory, you don't really get the concepts until you try them out yourself. And so for that, I'm going to ask you to prove some results, which we might or might not use in further videos, but it's good that you have a good grasp on them anyways. And so these are just things that I wasn't bothered to prove in this video, and so I guess that's why I'm setting it as homework. But you're going to have to prove them yourself. So yeah, try and prove the following properties on congruences. So this first one is kind of a warm-up. It's not that hard. Just if C is bigger than 0, then A is congruent to B mod M, if and only if CA is congruent to CB mod CM. So that's actually a pretty easy one to do. So I'll leave that to you, and I won't give a hint for that one. Next, a little bit harder. If the greatest common divisor of C and M is equal to 1, then CA is congruent to CB mod M, if and only if A is congruent to B mod M. So try and prove that one. And so you can see that's kind of, it's a little bit like this one, except now that we've got this coprime condition, we can actually reduce from CM all the way down to M. Now, to be even more general, you can let D equal the greatest common divisor of C and M, so that'll include 1, but it'll also include others. And then we're going to say that CA is congruent to CB mod M, if and only if A is congruent to B mod M over D. So these three exercises, you don't necessarily have to use the previous results, but they're all kind of related, I guess, because they all have to do with the CA, CB to AB, and when we can reduce or change between them. And so these are just generally nice ones to have in your toolkit. So what about this one? If A is congruent to B mod M, then the greatest common divisor of A and M is the same as the greatest common divisor of B and M. Okay, so that one I'll leave for you to prove as well. And then the last one, if A times B is congruent to 1 mod M, then the GCD of A and M is 1, and the GCD of B and M is 1. And so specifically, this is going to give us, if we set B equal to 1, we're going to have that A congruent to 1 mod M will give us this same coprimality result. But it's even more general here. Okay, so I'll leave you to prove those. And I'll put some hints in the description if you need them. So in the next video, we're going to be looking at more stuff on congruences. I mean, we're going to be doing congruences for quite a bit. And specifically, we're probably going to be looking at Fermat's Little theorem, Euler's theorem, maybe Wilson's theorem. So there's a lot of nice theorems to look at and a lot of nice proofs that are going to give us some really nice results. So I'll see you next time.